We'll see if that can start. Like our personal lives.
Okay, good morning. I'm going to review this reaction stuff and do just a little bit of new stuff, but wearing a mask and gloves because I did get sick Friday. Suffered all weekend. I'm getting better, but figured I could come in and do class. Maybe I'll cut it a little short, but I'm going to review reactions a little bit and add one new thing to reactions called theoretical years. But let me draw your attention to the quizzes. You can see it on the screen, but if you're watching the video, just realize I'm in the section on quizzes. I put things into categories, so all this stuff at the top you won't see. This will be all hidden from you. Yours will start with practice for test 1, pure math. So that's the significant figures, multiplication, division rule, addition, subtraction rule, scientific notation, just pure math. The next section is conversions and calculations, metric conversion factors, metric to metric conversions. Next section is the atom. So that was protons, electrons, and neutrons. I included isotopes in that section. All we've done with ionic compounds is formulas and naming, so that's in there. The only thing I've done with covalent compounds is some naming. How you formulate covalent compounds won't come up until test 2. And then there's the mole, converting to grams and moles, the number of molecules or atoms. So that's these two, and then I started reactions. So hopefully that helps, categorizing it like that. In some sense, test 2 will have this almost same structure, maybe not the pure math and stuff, but I'll say more about covalent compounds, more about ionic compounds, more about reactions. So I kind of cover the basics. That's kind of my approach. It's different from the textbook. The textbook covers every detail and gets to everything, and it's overwhelming. I like to cover all the basics, and then we go into the details after. So starting with reactions, I'm going to start as a review with example 7.4. This is chapter 7, section 7.4 is reactions. The beginning of section 7.4 talks about balancing. You're given the chemical equation and you have to balance it. I don't tend to make y'all do that because that's not the most important thing. Being able to use a balanced reaction is the most important thing. Maybe I'll have you balance some reactions later in the semester, but it's just not that important. So if you look at 7.4, it takes you through a process, and it's kind of the way I do it. So suppose most of the phrasing for these types of questions come down to, well, they all come down to, given the amount of one of the things that's there, how much of another thing that's there gets produced or is needed. So this says 37.8 grams of CO2, assuming that there's plenty of water. What is the mass of glucose? And it tells you above there what glucose is, right? The first sentence, glucose, and then, so you don't have to know what glucose is, it just tells you. C6H12O6. So this on the right side is the glucose. I told you given, this is, either given, we start with the easiest one. Either given moles of one thing and ask for grams of another thing. I mean, moles of another thing. You're either. That's the shortest, easiest type of these problems. You might be given grams of one thing and ask for moles of another thing. Or flip that around. You might be given moles of one thing and ask for grams of another thing. And then the longest calculation would be grams to grams. So realize that's always what it comes down to, these types of problems. And I've put these in order of difficulty. Difficulty just being how long the calculation is. And this is CO2, H2O. O2, 6O2. H12O2, there's only one of those. The other coefficients of 6 and 6. So if I closed my eyes and randomly picked one of these, let's say it was O2, and said that's what you were given. That's here. Let's say you were given O2 in one of these forms. And then if I limit O2 and I close my eyes and I randomly pick something, let's say I picked this. This is what I mean by this chart, H2O. This is one question you could get. You could be given moles of O2 and ask for moles of H2O. If you're given this and you're asked for this, the phrasing will be this much O2 is produced, how much H2O was consumed in the process. That would be the phrasing. If it was the other way around, then the phrasing would be this much H2O reacts, how much O2 was produced. So the phrasing is almost irrelevant. There's always going to be one thing and then another thing that you're asked for. The phrasing will be different depending on where the one thing is in this reaction and where the other thing is. You might even be asked these two. So those are both reactants. So then the phrasing will be, if this much CO2 reacted, how much H2O reacted? Or if it's these two that are involved, the phrasing will be this much O2, C6, 12O, 6O2. So these are both products. And then the phrasing would be, if this much O2 was produced, how much glucose was produced? So the phrasing is kind of irrelevant. It's always like this. You're given one thing and you're asked for the other thing. The phrasing will just be different depending on where the one thing and the other thing shows up in this reaction, whether they're both reactants, or it's reactant to product, or they're both products, or you're given product and given reactant. So realize that the phrasing is always kind of irrelevant. Just the way to think of it is you're always given one thing and you have to find the other thing. This one is asking grams to grams. This is the way kind of to start. Here's what you're given and here's what you have to find. The thing that you're given, you always want to write, what is that, 37.8 grams of CO2. grams. And I always just put it over 1. And you're trying to find the glucose, grams of C6H12O6. So you just look at the problem and you see what you're given. This is what you're given, that's this. And we're here. Well, I better, it's asked for grams, so we're here. Grams. Do that. So realize it's grams to grams. And the strategy here is to first go, if grams of something is mentioned, you're going to need the grams per mole for that thing. Meaning, grams of CO2 is mentioned, you're going to have to go, there's 1 carbon, there's 2 oxygens, 12.01 off the periodic table, 1.01 off the periodic table, 2.02, and I get 14.03 grams per mole for the CO2. So you're going to need that because grams of CO2 is mentioned. So for these, you're going to have to do this, find the grams per mole. Sometimes it'll be given, sometimes I just give you this to make it a shorter problem. But 14 grams of CO2, 1 mole. That's going to be needed. Grams of the glucose is also needed. Carbon, hydrogen, oxygen, 6, 12, 6, 12.01 off the periodic table, 1.01 off the periodic table, 16 off the periodic table. This I definitely need a calculator for. This one would be 12.12. That's going to be needed. That is 180.18 grams of C6H12O6 is 1 mole C6H12O6. So that's going to be needed too. The reason I know that's needed is because grams of this was mentioned. Grams of this was mentioned, grams of that was mentioned, so I need this and I need that. There's one other thing I'm going to need. I'm going to need the relationship from this CO2 to glucose. That is, I'm going to need yes.
For the, when you're finding the grams per mole carbon dioxide, how come oxygen was 1.01 and not 16?
Well, that's because I did it wrong. Thank you. 2 times 16 is 32. Yes, you're right. Oxygen is 16, not 1.01. Thank you. Where was it? So those things we're going to need. We always need this for these types of problems. When you're here, that's all you need. When you're here, you're gonna need that plus the grams of this, the grams per mole of this. And when you're here, you're gonna need this and the grams per mole of this. When you're down here, you're gonna need this and the grams per mole of both. But those three things are the ingredients we're gonna need to get all the way to the end here. And if you follow that, here's how you paste everything together. This much tells you that you're gonna need grams of CO2 on the bottom here. Okay, look here, and here, and here. The only place you see grams of CO2 is here. You don't see grams of CO2 here or here. You don't see grams of CO2 here or here. Once you have this, you look for the grams of CO2, it's here. So 44.01 grams is 1 mole. That tells you that moles of CO2 goes on the bottom next. We've used this, so we can ignore that now. Where do you see moles of CO2? You don't see moles of CO2 here. You see moles of CO2 here, so that's next. 6 moles of CO2. And this usually is in the very middle for these types. It is always in the very middle of these types. This tells you moles of the glucose goes on the bottom, but that's all that's left. 1 mole C6H12O6 to 180.18 grams. That'll do it. That'll give us grams. The rest is just calculated. That's exact. That's exact. That's exact. That's exact. That's exact. So these are where we get our significant figures. It's 3, 4, and 5. So our answer needs to be in 3. I have to make sure I divide by the 6 to do this. So I'll go 37.8 times 180.18 divided by 44.01 divided by 6. My calculator says
Did you get 25.79?
yes. 26. Thanks for double checking. 38, 37. That's exactly what my calculator said. I'm keeping 3 significant figures, the 9 rounds of 7. So 25.8. Okay, note, in the specific case, when you're given a reactant, write it down here. And I'm sure I said this, but it's just a definitional thing. The things on the left side here are the reactants. Those are the things you put together in a reaction vessel to have them react. This is the result. These are the products. So reactants and products. I'll use that phrasing. So you got reactant and product. If the one thing you're given is a reactant, specifically one of the reactants, and what you're asked for is a product, kind of small, but I mean that to be our next topic. So in the specific case, that something from this category is one of the reactants, and one of these things is one of the products, what you're actually calculating is called the theoretical yield. So really what we just did is calculated the theoretical yield of the glucose. If you're given a reactant and asked for a product, you're calculating the theoretical yield. We specify it that way because the vast majority of reactions, you don't get all of what you expect. You lose a little bit somewhere along the way. So you have a theoretical yield and an actual yield. The actual yield is what you find in experiment in a lab. The theoretical yield is what you're able to calculate given the input values of your reactants. So 7.5 is where this idea comes up. Let's see if we have one of these. So now I should write up here section 7.5. So in 7.5, you're going to be given reactants and asked for products specifically. Oh, and these types of calculations are almost always grams to grams. So let me do that. That's a good lead into theoretical yield. 7.5. Theoretical yield, and we have to go over the limiting reactant. So you've got two reactants. I'm looking at example 7.6. 2NO. NH3 and H2O. I'll remind you again what this means. One thing it means is those 6 relationships: 2 moles of NO to 5 moles of H2, 2 moles of NO to 2 moles of NH3, etc. But this coefficient is telling you you need 2 of those and 5 of these. And we can say moles. We need 2 moles of these and 5 moles of these, such that we will get 2 moles of these and 2 moles of these. Which you could say dozens, you could say scores, you could say individual, if you just put 2 molecules of these in the reaction and 5 of these in the reaction, then you will get 2 of these and 2 of these. But this idea of a limiting reactant, if I only put 4 of those in there, what's going to happen is all of these will be used up, and there will be some of these left over. See how we do this. So I'm going to split these H2s up into an H and an H. And I'll split these up into an N and an O separately. N and O. And I'll split these up. N, H, H, H. N, H, H, H. H, H, O. H, H, O. So let's see if we can do it. I need an N and 3 H's to make the first one of these. So I'll take that, and 3 of these, and then I'll move that. Now I'll take another one of these, and 3 more of these, and now I've made that. All right, let's make the HHO. HHO. Now I've made that. What I have left is HHO. No, I don't. I don't have any more H's left. All I have left over here is this O. I don't have any more H's. That's what I mean by some of this will be left over. In fact, this won't even get split up. And we won't even produce one of these. And we'll still be stuck with 3 of these. Unless we're able to use that O, this won't be split up. The point is, I guess we could still look at it like this. The point is, all of this gets used up, but there's still some of this left. That makes this the limiting reactant. Because we didn't have enough of it. I only had 4, not 5, and I needed 5. So that's the limiting reactant. Follow that? If I did it the other way around, it just got messy. To be able to do this reaction, I need 5 H2s. 4, 5. Such that I can make N, H, 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 O. All right, if I have 5 of these and 2 of these, I can make everything. But if I limit this one, now this one will get used up and I'll have some of this left. And then that makes this the limit. Meaning I can go N, 3 H's. There, I made that. I can make HHO. So I can make one of those. But that's it. This is used up. I have some of this left over, and I can't finish the reaction.
Aren't there 2 units?
There should be, but I purposely only put 1 to make this be limited. This is the bare minimum of each of these that we need to make it react. And if I limit one of them, the reaction won't go to completion. You look confused. Ask.
Yes.
What are you confused?
A little bit of everything.
I know that look. You don't even know what to ask, right? How else do I phrase this? I need at least 2 of these and 5 of these to make the reaction go to completion. I purposely only put one of these here, one of the NOs, to show you that you're gonna get stuck not being able to finish the reaction if you don't have enough of it.
But if we do have two NOs,
Then you're good. If I did have what I needed, I could continue. If I did have the NOs, then I could go take an N, 3 more H's, now I've got this, and I have just what I need to get.
so you're just showing like the theoretical if we didn't have enough.
Yes, I'm showing you what happens if one of your reactants is limited.
Okay.
Because this happens plenty.
Okay.
I mean, if you're a smart chemist, you put exactly the amount of this in and exactly the amount of this in, and you get the reaction to completion. But there are situations where one of the reactants is limited. We call the other one excess. But really the trick for limiting reactant is figuring out which one is the limiting reactant.
So we might have a problem where it's asking us to find the limited
Yeah.
reactant.
You have to find theoretical yield, you have to figure out which one is the limiting reactant first. The problems I was giving you in 7.4,
Yeah.
you just assumed there was plenty, that these were mixed in the perfect stoichiometric amount.
Okay.
Now we're looking at it where it's not going to be mixed in the perfect stoichiometric amount. One of the reactants will be limiting and one of them will be excess. So section 7.5 throws this sort of a twist into the analysis. This problem 7.6, it says we have 86.3 grams of NO. And H2, we have 25.6 grams. Given that, which one is limiting and which one is excess? So you have to answer that question first by looking at this. I'm about to show you how to do that. Oh, you guys want the camera? Okay. I remember how to do this. I have to answer this question. I just chose to do NO, the 86.3 grams of NO. I could have flipped this over and said, given that I have 25.6 grams of H2, how many grams of NO do I need? When I do this, I usually just pick the first one. But when you go through this process, you just pick one, just randomly pick one. I'll do this one first, and I'll do this one, and I'll show you that you come to the same conclusion. All right, here's how you answer this question. It's very similar to what we did in 7.4, but I need the grams per mole of NO. It's 14.01 times 16. First, I figure out the grams per mole of NO. That's what I'm putting here. 30.01 grams. So it is kind of a long walk. Limited reactant is kind of a long walk. Okay, and now I'm going to do the molar relationship of the reactants. I'm going to need moles of NO on the bottom. And I'm going to do moles of H2 on the top. Moles of NO on the bottom because moles of NO is up here. 2 moles of NO to 5 moles of H2O. And now I need the grams per mole for H2. That's 1.01 times 2, which is 2.02, meaning 2.02 grams of H2 is 1 mole of H2. So it's kind of a long walk, but what I'm answering is this question. Given that I have 86.3 grams of NO, how many grams of H2 do I need for it to be mixed in a perfect amount so that everything will react? So there'll be no reactants left over. That's the question I'm answering. If you go through all of this, 86.3 times 5 times 2.02 divided by 30.1 divided by 2, and I get, I guess I'll do the significant figures, which will be 3. Okay, I've answered the question. At a bare minimum, I need 14.5 grams of H2. You see what I've done? I've answered this question. Given that I have 86.3 grams of NO, how many grams of H2 do I need? At a bare minimum for the whole reaction to go. Do you see that? Now that I've found out, look at how many grams of H2 the problem said it had. We have way more than we need. You see that? The actual reaction mixture was mixed this way. I really only needed 14.5 grams of H2. I had way more than I needed. Do you see? This answered that question. How much did I need? 14.5. How much did I have? A good bit more than that. What that tells you, that's in excess. If that's excess, that means this is limited.
So, if you ask that question, like given that I have, like how many grams of H2 do I need, do we have to put how much excess we have as well?
You could say, here's how much I do have in excess. That minus that. I have 11.1 more grams than I need.
Okay.
So from that, would you be able to determine that H2 is or is not a limiting reactant?
Yeah.
Okay.
Well, we've determined that it is not.
Yeah.
We found out that it was in excess,
So if you had,
which means the other one is necessarily limited.
so if you had more than 25.6, or if you had less than you needed?
If I had less than this, then it would be limited, and the other one would necessarily be in excess.
I gotcha. Okay.
But I just chose to do NO2.
Right.
You just pick one.
Okay, I have a question about the equation itself, and this could just be
This,
well, during your your process. Now you have 2.02 grams of H2. Do we not multiply that by 5? You see what I'm saying?
this is sort of theoretically the way the reaction works.
Okay.
This is how it was actually done.
Okay.
So we have to follow this. Someone walked in a lab and put this many grams of this and this many grams of this. They did it kind of wrong, because all they had to do was get 14.5 grams of this. But that's the question.
Okay, so I'm asking on your before, where it's 2.02 over 1 mole, you don't multiply that 2.02 by 5.
No.
You don't, but in the previous equation we did 7.4, we calculated the grams of glucose. You see what I'm saying?
Well, we didn't have to find limiting in excess.
But that's, so
It's-
for the limiting excess, we don't need to calculate how many grams are in H2 in the problem. Or is that?
Well, let me put it
because
this
that's what
way.
we're finding?
The grams of H2 are given to you here.
Okay, I see, because we're finding it. Okay, I see.
You sure?
Yes.
All right. Ask me outside of class if you still.
Okay, I will.
Okay. But notice, I just chose to use NO here. What I want to do is go say, what if you decided to use H2 and answer this question? What I'm saying is you'll come to the same conclusion, so it doesn't matter which one. I usually just grab the first one and go with it. But notice, I can answer this question by doing H2. Given that I have 25.6 grams of H2, how many grams of NO do I need? So I'm just going to show you, you come to the same conclusion. You'll still discover that that's excess and that's limited, even if I go through this process for the other reactant. I'm told I have 25.6 grams of H2, grams of H2 on the bottom. This is going to be the grams per mole. That means moles of H2 is on the bottom, because moles of H2 is actually going to be moles of H2 down here. That's this 5 moles of H2 for 2 moles of NO. And then last, I need moles of NO, and that's going to be this 30.1 grams. So that's going to tell me how many grams of NO I need, given that I have 25.6 grams of H2. All right, 25.6,
Is this 30.01, not 30.1?
yes. 25.6 times 2 times 30.01 divided by 2.02 divided by 5. It's 3 significant figures, so I guess that's all I need. 152 grams of NO. All right. We need 152 grams of NO. We have 86.3 grams of NO. We don't have enough. That's how many we need to react with this many grams of H2. This is what we need. This is what we have. 86. We don't have enough. This is what we need. Given this many grams of H2, that's how many grams of NO we need. But this is how many grams we have. This is what was given in the problem, these two values. Since we don't have enough, this is limiting, which necessarily makes that excess. We come to the same conclusion regardless of which of the reactants we go through this process.
Is that going to ask you for numerical value?
What about numerical value?
Like, is that going to ask you for one? Is it going to ask you for anything like that, or is it just going to ask you for one?
Yeah, it's generally you're not actually asked for this.
Yeah.
Going through this process is really kind of chapter 7.4, where you're not thinking about the limiting reactant. That would be the answer to something from 7.4. Now that we're doing limiting and excess, you just calculate this en route to figuring out these two facts. Okay, here's the point. Figuring out which one is the limiting reaction tells you that I didn't write that big, but that's the whole point. Now that we found which one is the limiting reactant, we're going to use that one to predict amounts of products. So if you want to know how much NH3 is produced, you're going to use the limiting one. If you're asked to find out how much NH3 is produced, you're going to use this. Or if you're asked to find out how much H2O is produced, you'll use that. You don't use this to predict products because that one was in excess. You use this to predict amount of products. And from there, it's just like 7.4. You take the grams of this and you use this to find the grams of these. You do the grams of reactant, the grams of reactant is specifically, you're using the grams of the limiting reactant to predict products. That's the whole point of finding limiting reactant. You guys okay? I have problems up here for these. I'll get them quick though. I have some already made. I meant to do that this weekend and I just couldn't do anything. Limiting reactant. Let's find finding these coefficients, that is balancing a reaction, it's called stoichiometry, stoichiometric amounts, just a vocabulary so you know what that is. All of them want you to balance. Where's the limiting? There it is, okay. Where's one in grams? Doing everything in moles, come on. Cut it out. Okay, number 62 in the exercises. TI plus 2F2. Oh. I should have said this again. When you find this grams in products, that's the theoretical unit. How much you theoretically should get in a reactant. TI at 2. fluoride, titanium 4 fluoride. Okay, you're told in A, you've got 5 grams of titanium and 5 grams of F2. And believe it or not, this happens a lot where you mix things not in the perfect stoichiometric amount. All right, so the question is, what is the theoretical yield? That is, how much product? Theoretical yield is how much product is. The theoretical yield is how much product is expected. But we have to go through the process to figure out which one of these is excess and which one is limited. Missing a 2 here. So I'm just going to start with the TI and I'll use that. The question I need to answer is, if I have 5 grams of titanium, how many grams of F2 do So let's start with just look on the periodic table for TI. Anyone got their periodic table?
47.867.
7 grams is 1 mole. So that's straight off the periodic table. Now we need F2. What's the molecular weight of fluorine?
18.998. But that's not times 2, that's just 1.
Or times 2 is,
I can't do that in my head.
I can't either.
37.996.
So this is the grams per mole of titanium. This is the molar relationship here. So it's 1 mole of TI, 2 moles of F2, and then the grams per mole of F2, 37.996. This is going to tell me how much F2 I need. Times 2, 37.996 divided by 47.867. I get 7.94. That's how many grams of F2 I need if I have 5 grams of titanium. So what's our conclusion here? We need 7.94. We have only 5.
Fluorine is your limiting reactant.
So this one is limiting. This one we're going to say is in excess. But that tells us we're going to use this, more specifically this 5 grams, to predict that. We're not going to use the 5 grams of TI, meaning we're going to use 2 moles of F2 and 1 mole. We're going to use that to predict the product. These limiting reactant things and theoretical yield. So we're calculating the theoretical yield of this. We have to use the limiting reactant to do that. So we just went through the process to figure out which one is limiting. Now we can calculate our theoretical yield of TiF4. So we're going to go 5 grams. 0 grams F2. $37.996. That gets us to moles of F2. It's 2 to 1, 2 of these to 1 of these. Now we need and TI was, did I erase it? What was TI off the periodic table?
It is 47.867.
47.867. And what is 4 times 18.998?
75.992.
9, 15. I think I did that right. 123.859. That'll tell us how many grams of TiF4 we could expect to get from this reaction. That is the theoretical yield. 5 times 123, 859, divided by 37.996, divided by 2. So if I did that right, it's 8.15.
What's your like
Let's set a picture.
Yield always refers to the products. That's our theoretical yield. That's our theoretical yield. So we went through all of that to find out how much product we would get. It is a long walk.
So, would it, like, on a test or something, would it be like a 2-part question saying, like, first find, like, the limiting, and then...
I don't tend to do 2-part questions. What I do is I would have the easier question where I would just ask which is excess and which is limited.
Okay, all right.
And then I'll have a completely different problem that has you follow all the way to the end. You see what I mean?
Yes.
But since it's just theoretical, the limiting reactant wouldn't affect, like, the fact that if you have one that's limiting wouldn't affect the theoretical yield, right?
No, the fact that one of them is limited doesn't affect the theoretical yield. The only twist is once the reaction is done, you'll have 8.14 grams of this, and you'll still have some of this left over from the reactions, which is a problem because then you have to separate this out. But frequently you can, like this is a solid and this is dissolved in solution, so you just filter it. So this is what I mean by sometimes we purposely make something in excess to be sure we get as much as we want here, and then we just separate it again. Let me make one more point. This thing about limiting and theoretical yield. Theoretical yield, that's a long calculation. There's something called actual yield. That's usually very, very easy. It's simple, it's given. And then there's a percent yield. I'll just say fairly easy calculation. What did we decide? In this case, we have 8.14 grams. So the sum total is, sometimes we get a question like this, and I'll get some up. Then you go through all this, and it says, it gives you the 5 grams and the 5 grams, but it also tells you that, let's say, everything in that problem, camera, will you? Well, tell me if you want the camera back. Let's say this problem said, yeah, it was, and it was 5.0 grams of F2. And sometimes it will say, the actual yield of TiF4 was, and then it'll say, so I spent most of this time talking about the theoretical yield because that's the long walk. The rest of this is pretty straightforward. Actual yield, if we did we actually did a lab in here, and you, at the end of the lab, you weighed your product and you looked at the scale and you went, that's how much it got. That's what the actual yield is. It's literally what you see on the scale at the end of the experiment. If this was the actual yield, what was the percent yield? What you have to figure out is you have to find the theoretical yield, which is the long walk. But if we find out that our theoretical yield was this, and our actual yield was 0.96 grams, the percent yield is just this. That's how you find the percent yield. Actual was 7.96 grams. Theoretical was 8.14 times 100%. So, and it is typical that you lose a little bit of your product for whatever reason. It's rarely everything works out perfectly. 1/4 times 100. Divided by 8.14 times 100. in that case, you would have 97.8% of what you expected to get. This is the percent yield. That's your actual yield, that's your theoretical yield. That made the percent yield. So realize for all these concepts, the actual yield and the percent yield are pretty simple ideas. The theoretical yield is the long walk. You gotta find your limiting reactant, and once you find that, you gotta predict your product using the limiting reactant. And then you've got your theoretical yield. And then the actual yield is usually just given. A problem might say, 5 grams of this, 5 grams of this. The percent yield was 97.8. What was the actual yield? But still, the long walk is to find the theoretical yield. And if you're given this, then you just use algebra to find the actual yield. So theoretical yield is the long walk. The rest of this is pretty simple. You confused?
No, it's the long walk.
Yeah, it's the long walk. I don't mind reviewing this more. I need to get some problems up for you on this. But I'm going to stop there because I'm sweating. I'm feeling good. Y'all are way ahead. My Monday, Wednesday class, who missed because it's a long class, and they're way behind compared to y'all. So we're in pretty good shape. So I'll just